Hi, let's have a look at this question here. Physics standard level and high level. This question came in paper 2, time zone 2, May 2022, number 5. So let's see what do we have here. An experiment is carried out to determine the count rate corrected for background radiation when different thicknesses of copper are placed between a radioactive source and a detector. The graph shows the variation of corrected count rate with copper thickness. Part A outline how the count rate was corrected for background radiation. So this is a 1-mark question, should be a straightforward, but let me give you some insights here. So first of all, let's see what do we have on the y-axis. So we have the corrected count rate in count per minute, which we call the activity. Okay, so the activity is the number of decay per unit time. Here, that unit time here is minute. I need to watch for that because, I can use minute no problem as long as, it is consistent in the calculations. Otherwise, we need to do some conversion because, the SI unit of activity is basically becquerel, BQ. So BQ is basically decay per second, per unit time in SI system, which is decay second minus 1. Okay, so that is becquerel, but obviously here it is not becquerel, it is count per minute. Now, on the x-axis, we have the copper thickness in millimeter. Now let's review together what do we mean by background radiation. So the background radiation is a radiation that exists in our environment in the background already without any specific radioactive source, right? And these are basically the sources of this background radiation. For example, you have radon gas, found in soils and rocks. Cosmic rays, food and drink. Cosmic rays are very high energy charged particles coming from the sun or other stars in the solar system. Okay, so cosmic rays are high energy charged particle stream, right, coming from the sun or other stars. Now there are some artificial sources here like medical. Obviously the main portion here is medical, right? Hospitals, whatever, clinics, and then power station or nuclear power station. Okay, so what we normally do to correct a certain reading or certain activity, we need to subtract, of course, the background radiation from the total given activity, and this is basically the answer to part A. So what I would say, okay, so the count rate, I don't know why I'm writing with the pink color here, it's fine. So the count rate was corrected by subtracting the average. Let's say you took some few readings, for the background, and then it took the average. This is what you normally do to reduce the random error. So the average, so by subtracting the average background radiation, and you may add like such as, just to give it a little bit of information here. Yeah, so such as, let's say, cosmic rays and radon gas. Okay, so that is the first question. Now part B, when a single piece of thin copper foil is placed between the source and detector. Now the count rate is 810 count per minute. So see here, now the question here is given in count per minute, which is consistent with what do we have on the y-axis. So in this case, I do not need to do any conversion, but of course, as a tip, you always need to make sure the units are consistent, or otherwise you will need to convert, right? Now the foil is replaced with one that has 3 times the thickness. So 3 times the thickness, when it was 810. Now estimate the new count rate. So what we can do here it's just a graph like reading the curve here. So let's place 810. So we have from 0 to 200 here, we have 5 squares. So that means each square is 40, right? 200 divided by 5 is 40. And then, okay, so this is 800, this is 840. So 810 is just a very, like a small distance, like quarter of this distance here between 800 and 840. So then you hit the curve, you know, and then go down to read the thickness first at this count rate. So it is, okay, so again, let's read the scale. So I have 0.5, I have 5 squares. So 0.1, 0.2, 0.3, 4, and 5. So it is between 0.2 and 0.3, right? So I feel comfortable to say, okay, it is like 0.25, just in the middle between 0.2 and 0.3. Now, 3 times the thickness, so 0.25 times 3 is 0.75. So what you're going to do, you're going to do the same thing, but backward. So at 0.75, you know, you hit the curve vertically, right? So you hit the curve. Yeah, sorry, just let me get the straight line here. And then go horizontally. It is less than 400. So it is between 360 and 400 because again, each square is 40. If you tell me, okay, it is 380, I'm fine. 370 is fine. 375. You know, you try your best. Okay, so let's say 375. Okay, so 375 count per minute. And usually in the market scheme, there is a range of accepted value. So don't worry if you are like within the range, your answer will be accepted. You don't want to be really way off, you know, just reading the scale and be as accurate as possible. Okay, very good. Now, part C, further results were obtained in this experiment with copper and lead absorbers. Comment on the radiation detected from this radioactive source. So basically what we need to do here is to guess what kind of radiation is there, right? Comment on the radiation detected. So now let's say first, okay, let's read first the table. So you have copper and lead, I have the same thickness, millimeter, but then the count rate is less in lead compared to copper. So this could be an observation. Now this is 4 marks. This is 4-mark question. So what I would like to do is just to, you know, lay out your answer in points. So each point will have like a mark, right? So the first mark, you know, I will just say observation. I will just say observation here, you know, like since the corrected count rate, for lead, right, is less than that for copper, okay, given the same thickness, so that means the lead is a better absorber than copper. Okay, just a simple conclusion, observation, right? So you can say, okay, so lead is a better absorber than copper. Now let's review together, okay, what kind of radiation do we study or did we study in the program? The topic 7, atomic physics. So basically we have 3 or 4 types of radiation we covered, right? Alpha radiation, beta minus and beta plus, and then gamma ray. Okay, when I say beta radiation, by default is beta minus radiation, which is like a very fast electron. But here in this case, we're gonna focus, or we need to review the property of the penetrative power or the power of penetration. So how far each radiation can, can pass in certain medium. So alpha particle, has the least penetrative power, a few centimeters of air. So obviously, when we talk about here copper and lead, like metals, so obviously alpha is not here at all. Okay, so we can say here as another conclusion, a second conclusion here, alpha, okay, is not a possibility. Alpha particles, if you like, alpha particles, alpha radiation, is not a possibility, right? And if you would like to add, okay, since alpha has the least penetrative power or depth of penetration, so therefore alpha, and then of course we talk about, metals, like, actually alpha particles could be stopped by a piece of paper. By a thin piece of paper, alpha could be stopped. It has the highest ionization power, but it has the lowest depth of penetration. Now, the second conclusion here, so again, let's continue. So I have beta minus particle or beta decay, a few millimeter of metal, right? And then gamma ray, many centimeter of lead. So if gamma ray, can penetrate many centimeter of lead, and we have here 3.5 millimeter only of lead, so obviously there is a gamma ray, right? And the gamma ray could not be stopped, obviously, by also the same thickness of copper, because lead is better. Lead is better absorber, right? So we can say, okay, maybe gamma radiation, right, is the main type or source, right, of this, is the main type in this radioactive source. Okay, so gamma radiation is the main type detected, let's say, right, by the source, by the radioactive source. Okay, but since we have lead, but then gamma even can go even few centimeter of lead, so it has the highest penetrative power. Now beta, you may actually say beta could be stopped by few millimeter of metal, so we can say there is no beta at all. Okay, because a thickness here, even 3.5 millimeter of copper could stop beta, right? Of course we don't know how many, but few millimeter of metal can stop beta. So one alternative here, we can say beta, right, is stopped or could be stopped, right, by few millimeter of metal. Okay, copper, aluminum, whatever. Or the other possibility here, you can say, okay, but maybe the thickness here is very small, like 3.5 millimeters. So maybe there is a certain percentage, of beta particle decay could pass, because again, here the thickness is tricky. Here is very small, is 3.5, just 3 millimeter or 3.5 millimeters. So, right, both answers are correct. So now this is basically how most important, we want to see your analytical skills. Okay, how you lay out the observation and then the conclusion in these 4-mark questions. And of course, we test your knowledge on the radioactive types or decays. Now, last part here, part D. Another radioactive source consists of a nuclide of cesium CS-137 that decays to barium Ba-137 as well. So 137 here is the mass number, and we call it the nucleon number, which is the sum of protons and neutrons. And the definition of nuclide, a nuclide by definition is a particular nucleus of a specific number of protons and neutrons. Okay, so this is like a kind of fancy name of nucleus. Okay, so nuclide is a particular nucleus with a specific number of protons and neutrons. This is one of the definitions in topic 7. Anyway, so we need to write down the reaction of this decay. So we're starting with CS. Now, the number at the bottom is the atomic number, 55, which is the number of protons, right? And then this cesium here is decayed into barium 56 and 137. Okay, so in order to write down this reaction, we need to understand what's going on here, right? So the 137 here is the nucleon number and did not change, which means it's not alpha, because alpha is a helium nucleus, 2 protons and 2 neutrons. So if it was alpha, you would see a change in the nucleon number. However, here, if the nucleon number stays the same, so we are looking here at either beta minus or beta plus decay, right? So we can actually, very easy, we can just say, okay, what is the number here to balance? So we need to balance the atomic number on both sides. So if you have 56 here, so I need -1 as a charge, which is an electron with 0 relative mass, right? You can write this. So obviously this is beta minus decay. You can write like that, or you can write beta minus and 0. And then since it is a beta minus decay, so it is always associated with an anti-neutrino. So this is how you, the symbol of anti. So anti-neutrino, you have to write the bar, and maybe you can say sub E, right? You can leave it like that, or you want to put 0 and 0, it's up to you. But this is basically the reaction. So neutrino is, or anti-neutrino is a subatomic particle, right? I can talk about particle physics in a later video, but I mean, what you need to know about the beta minus decay, it is always share the energy with neutrino or anti-neutrino. If it's beta minus, so it's going to be anti-neutrino, and the neutrinos are subatomic particles with 0 charge and very, 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 very small non-zero mass. Okay, so sometimes in the symbols in textbook, you know, they kind of approximate this and they put 0 and 0 up and down, but technically the neutrino has non-zero mass with 0 charge. Okay, so I hope, yeah, that's it for question number 5. Okay, I hope it was a good revision for topic 7, atomic physics. And if you have any comments and questions, please feel free to leave them in the description. And in the meantime, have a nice day.